Hello everyone. In previous lecture, we have talked about Gauss law. We have seen in detail what is Gauss law and how Gauss law can be formulated. So in this topic, we will see the application of the Gauss law. So before starting the application of a Gauss law, basically Gauss law is used to find out the electric field for any symmetrical surface. Electric field determination of symmetrical shape. So we will discuss the application of the Gauss law in this topic. So first we will see the electric field due to infinitely long, straight, uniform charged wire. So basically we talk about uniformly charged wire. So it is one dimension, only the length is considered here. So for that we will see the lambda. Linear charge density is used to calculate the electric field. Then we will use to find out the field for uniformly charged plane sheet. So it is here two-dimension figure is this, where length and breadth are the important factor. In this case, we use surface charge density, and last is the field due to uniformly charged solid sphere. So in this case, we will see the sigma, which is equal to charge upon volume. So it is basically three-dimension figure is this. So we will see the application of a Gauss law in this one dimension, two dimension, three dimension figure. So in this we will talk about how can we apply Gauss law for any symmetrical surface. So basically we follow three different steps. First, we will identify the surface and draw the symmetry. So in this case, we will draw a imaginary Gaussian surface. Imaginary Gaussian surface such that it is symmetrical around the shape, around the object. Second, we will count the charge and calculate the electric flux. In the previous step, we will draw the Gaussian surface. In this step, we will calculate the net charge inside the Gaussian surface. And after calculating the net charge, we will apply the formula for the net electric flux. E dot dA. So when we apply this formula, we need to find out the angle between E and A. So basically in this we will go to the two cases. Either both are parallel or both are perpendicular to each other. Depend upon the scenario to scenario, we will see when it will be parallel and when it will be perpendicular. And in the last step, we will apply the Gauss Law equation and solve the electric field. We have seen the Gauss Law equation. It is like this. Phi is equal to Q enclosed upon epsilon naught. And the whole purpose of this to find out the electric field. So basically, we choose electric field in such a manner where we can separate out it from the original equation, that is E dot dA. So we will separate out the E from this flux equation and equate it with the original one. E can be calculated like this: Q enclosed upon epsilon naught into 1 by dA. So we will see the application for a infinitely long, straight, uniformly charged wire. So in this case, we will take a charge wire which is having of infinite length. Due to this, we will calculate the electric field. So in order to calculate the electric field, we will apply the Gauss law. Now, we need to find the electric field at a distance r from the line of a positive charge of infinite length and constant charge per unit length. So in the given figure, we will go through it, and we will see how the actual symmetry is going to work to find out the Gaussian surface. It is the view of electric field at the bottom of the cylindrical surface, which is of constant magnitude and perpendicular to the surface. We will talk about it in later. So this is our main figure here. This is the uniformly charged wire around which we will draw a Gaussian surface. So cylinder that we have seen, this is supposed to be our Gaussian surface. So in the Gaussian surface, we need to find out the detail from where the electric flux is coming out. So in this figure, we have three surfaces that we will consider to find out the electric flux. First, this surface. Second is the this one is the bottom figure. Bottom and top. And third one is this curved surface. So though we can write the net flux is equal to flux due to surface number 1, flux due to surface 2, and flux due to surface 3. In the case of surface 1 and surface 2, for the surface 1, it is like this, and the area vector is normal to the surface. It is like this, and electric field is in this direction. So by observing the figure, we can observe that here area vector in this case area vector and electric field are perpendicular to each other. So same thing will be occur with surface number 2. Here area vector and electric field are perpendicular to each other. So we can write E dot dA cos 90 plus E dot dA2 cos 90 and E dot d3 cos theta. For the surface number 3, we have seen that electric field and area vector, they both are parallel to each other. So in this case, electric field and area vector are parallel to each other. Parallel. So here theta is equal to 0 degree. So by putting all these value, we will get this term will lead to 0, this term will lead to 0, and this term will be given by given like this. B, separate out the E. Here it is dA, and here cos 0 is equal to 1. Now, when we obtain this equation, we will apply Gauss law. So, by applying the Gauss law, it is like Q enclosed upon epsilon naught. So, as we know that the lambda is the linear charge density. Per unit length. Let us suppose this rod carry a charge Q, total charge stored by wire. Then we can write lambda is equal to Q by L. Further we can write Q is equal to lambda into L. So putting this value, we will get lambda L into epsilon naught. So this is question number 2. On solving question number 1st and 2nd, we will get E dot dA is equal to lambda L into epsilon naught. So as we know that the area of cylinder is equal to 2 pi r into L, where L is the length of cylinder and r is the radius of cylinder. So on the putting this value, we will get E into 2 pi r equal to lambda L upon epsilon naught. On solving this, we will get E is equal to lambda by 2 pi r epsilon naught. So this is the desired expression for electric field due to long infinite charge wire. Or we can also write two k lambda by r. This is also the expression for electric field, where k is equal to 1 by 4 pi epsilon naught. Now, in this, we will see how the electric field can be calculated due to plane sheet. So basically, plane sheet is a two-dimension figure. Plane sheet is a two-dimension figure. So in this case, we will find the electric field due to non-conducting an infinite plane sheet of positive charge with uniform charge density. Here, sigma is the uniform charge density. So in this case, the plane sheet is infinite and it is non-conducting. It is infinite and non-conducting. So this is our plane sheet, and plane sheet is uniformly charge distributed, and it is also not conducting. So here the electric field, in this case, it is lower to the surface like this. Here electric field will be normal to the surface, and we need to find out the magnitude of the electric field. So our first priority is to draw a imaginary Gaussian surface. So in order to draw a imaginary Gaussian surface, we will consider a small cutout of certain radius. And from this cutout, we will draw a imaginary Gaussian surface of equal length on both sides. We will take n length from this side. Also, we will draw imaginary Gaussian surface on this side too, of same length. This is our Gaussian surface. So we have wrote that is cylindrical Gaussian surface penetrating infinite plane of a sheet. The flux is EA through each end of the Gaussian surface and 0 through the curved surface. So in this case, we have going to find out the net flux through three different surfaces. First is this surface, second is this surface, and third is this curved surface. Curved surface. So we will find the net flux due to first surface, second surface, and surface number third. So as we have seen that for the surface number, for surface third, let's suppose our area vector is like this. Area vector is like this, and electric field, as we discussed, it is normal to the surface. So electric field is in this direction. So by observing, we have seen that for this case, here area vector and electric field are perpendicular to each other. Perpendicular to each other. For the surface 1 and surface 2, the area vector and electric field are parallel. So in both the case, if theta is equal to 0 degree and here theta is equal to 90 degree. So phi 1 is equal to E dot dA1 cos 0, phi 2 equal to E dot dA2 cos 0. So by symmetry, dA1 is equal to dA2, and for the phi 3, it is E dot dA3 cos 90, which is equal to 0. So finally we can write E dot dA plus E dot dA. On solving this, we will get 2E dot dA. Let us suppose this is question number 1. So by applying Gauss equation, phi is equal to Q enclosed upon epsilon naught. So here that Q enclosed is equal to total charge upon area. So we can write Q is equal to sigma into A. So we can write further, here Q enclosed is equal to sigma A upon epsilon naught. So let us suppose this is equation number 2. On combining equation first and second, we will get is equal to sigma A upon epsilon naught. So let's suppose the integration of this is BA. So we can write 2A into A equal to sigma A by epsilon naught. So on solving this, we have obtained the net electric field is equal to sigma by 2 epsilon naught. This is electric field due to thin infinite plane sheet. Now, in this case, we will find out the electric field due to uniformly charged solid sphere. Here the sphere is solid. It is not hollow. It is completely filled with some object inside. So in this case, an insulating solid sphere of radius A. Here the radius is A, has a uniform charge density, volume charge density, which is equal to rho, and it carries total positive charge of Q. So we can write Q is equal rho is equal to Q upon volume. So Q and volume of the sphere should be 4 by 3 pi a cube. So we are going to use this formula to calculate the net electric field due to solid sphere. So we will calculate electric field at two different positions. First, at the point outside the sphere, and second, at the point inside the sphere. So this is supposed to be our sphere of radius A, and we need to find out the net electric field at this point, which is outside the sphere. So let us consider R with the point, R the distance from the center where we need to find out the electric field. And this blue line is indicate Gaussian surface. Gaussian surface which must be symmetrical to the charge distribution. Now, in the other case, we will find out the electric field at a point, this point, which is situated at a r distance from the center. So here r is greater than a, and in this case r is less than a. So in the both, the blue line is indicated the Gaussian surface. This is our Gaussian surface and this is our Gaussian surface. So first we will go for outside. Since we have seen in earlier videos that electric field due to at a distance r can be given by kq upon r square. So in this case the total charge is equal to q and the distance is r from the center. So this is the net electric field it is net electric field outside the sphere at distance are from the center. So this is our final expression, and this is the condition where r is greater than radius of the sphere. Now we will going to see the electric field inside this sphere. Now electric field inside the sphere at a distance r from the center. So the first step is to write net flux is equal to E dot dA. So from the figure we know that here the direction of area vector and electric field are same. So we can write they are parallel and theta should be 0 degree. So we can write phi should be E into dA. So here area we will consider this area which is less than the area of a sphere, total surface area of the sphere. So let us consider Q dash is the charge stored within the Gaussian surface, and Q is the total charge stored. Total charge stored. So by the symmetry we can write rho is equal to Q by V equal to this is equal to Q dash by V dash. Here the Q dash and V is 4 by 3 pi r cube, and here Q is equal to 4 by 3 pi a cube. So on solving this we obtained Q dash is equal to Q r cube by a cube. So we are going to utilize this formula in our case. So this is supposed to be question number 1, and by applying Gauss law, phi is equal to Q enclosed upon epsilon naught. Here the Q enclosed is equal to phi dash upon epsilon naught. So we can write phi is equal to rho into betas upon epsilon naught. So this is question number 2. So on combining question number 1 and 2, we will get A into dA is equal to rho, and here the volume V dash upon epsilon naught. So as we know that the total surface area of can be 4 pi r cube r square. So putting this value, we will get E into 4 pi r square, and we will write rho can be written like this. V dash epsilon naught into V dash. So we will cut out this. We will obtain the value of Q R cube epsilon naught into A cube. So finally we can write electric field is equal to Q R cube four pi r square epsilon naught into A cube. So on solving this, we will get QR 4 pi epsilon naught into A cube. This is the expression for net electric field due to solid sphere inside the sphere. It is inside. And here R is less than the radius of the sphere. So that's all in this video.